So here's our first example for graphing functions. The instructions say graph each function by plotting appropriate sample points. And then part A gives us f of x equals 2x plus 1. The first thing I'd like to point out is that this is a linear function. How do I know it's a linear function? Well, the x is to the first power, and there's nothing else funny going on. There's no denominators, there's no square roots. Okay, so a function that just has x to the first power is a linear function. Right? Next, we need to talk about what sample points to use. Okay. I would suggest starting by using -2, -1, 0, 1, and 2. Okay, those are good sample x values to start with. Right? Now, for some functions, those sample x values will not work. Okay, and we'll talk more about when they don't work in the last 3 examples. But for now, let's go ahead and plug in x equals -2, -1, 0, 1, and 2 and see what y has to be. So it's a good idea to make a little table to help you keep track of all the information. All right, in the left column of the table, put the x values you're going to plug in. In the next column, go ahead and plug those x values in. And then finally, figure out what point that tells you on your graph. Okay, so when I plug -2 into this function, I'm going to get 2 times -2 plus 1. So -4 plus 1, which is -3. When I plug -1 into this function, I get 2 times -1 plus 1, which is -1, etc. So let me go ahead and put the work for the rest of them without talking about it. So there's my y values. Okay, I took each of these x values, -2, -1, 0, 1, 2. I plugged them into my function for x. Okay, I put in -2, -1, 0, 1, 2 right into this given function, and then I calculated what my y values had to be. So then each of these gives me a point on my graph. The first line here tells me that -2, -3 is on my graph. Then -1, -1, -1, -1, etc. So here are all my points. Okay. So finally, to get the graph of the function, I have to plot each of these points in my xy plane and then connect the dots. Because it's a linear function, this should end up looking like a line. Okay, but let's see what happens. -2, -3 means I go -2 on the x-axis, -3 on the y-axis, put a point. -1, -1, right? -1 on the x, -1 on the y. 0, 1, 1, 3, 2, 5. So there's all my sample points, and it's looking like a line, so that's good. Let me go ahead and connect the dots, because the entire function is not these 5 points, right? The entire function goes on forever. It's a line. Okay, so these 5 points are not the function. You need to connect the dots with a curve in order to get the final graph of the function. So there's the entire function. There's the line that goes through my 5 sample points. Of course, remember, this goes on forever. Okay, so we want to indicate that this function is going to continue forever in both directions, so we put arrows on the end of our curve here. So that's the graph of the function f of x equals 2x plus 1. This shouldn't surprise you. Okay, we didn't actually need to plot points to graph this particular function if we notice that it's a line. Right? Remember, this 2 in front of the x is telling me that the slope is 2 if you think of this as y equals mx plus b. So I should know that my slope is 2 and my y-intercept is 1, which means I could start at 1 and go up 2 over 1. So this particular function can be plotted more efficiently by using slope-intercept form. But in general, plotting points is the method we're going to use for more complicated functions. Let's go on to the next one. Alright, on to our second example, which gives us the function f of x equals 5 to plot. This, hopefully you recognize, is a constant function. Okay? Because there is no x on the right side, there's no variable on the right side at all, we know this is a constant function. Alright? So let me go ahead and pull up my table and plot my usual sample points, and we can figure out how this looks. Okay, so here we go. I have -2, -1, 0, 1, and 2 to plug in for x. Now, there is no x on the right side. Okay, so don't be fooled. This is much simpler than students want to make it. When you plug -2 into this function, it's 5. When you plug -1 into this function, guess what? It's still 5. When you plug 0 in, 5 again. When you plug 1 in, 5. When you plug 2 in, 5. That's how constant functions work. They're constant. No matter what x value you plug in, the y value doesn't change. So our points are very straightforward. -2, 5. -1, 5, etc. So we can go ahead and plot these points to get a good idea of the shape of our function. So -2 on the x-axis, 5 on the y. So here's -2, 5. -1, 5. 0, 5. 1, 5. 2, 5. Okay. So our sample points are showing us that we have a function that's a horizontal line. All constant functions are horizontal lines, so that doesn't really surprise us. So let's go ahead and connect the dots and put our arrows on so we can have the entire graph of this function. So there's our constant function. It is always 5. No matter what x value you plug in, the y value will be 5. That's what this tells you. Cool. On to the next one. Alright, here's our third function to graph. F of x equals -x squared plus 3. I want to point out right now that the x is getting squared. That makes this a square function. One advantage of recognizing what type of function you're dealing with is that you know the general shape that you should get out of your points when you plot. Because this is a square function, I know my final graph should look like a U shape. Square functions always have this same general shape. Right, but let's go ahead and do the dirty work. Let's plug in our x values, -2, -1, 0, 1, 2, and see what happens to our y values, to our function values. So when we plug -2 into our function, we're going to do negative, because the function has a negative in it. Then we're going to put -2 in for x. Then we're going to square. Then we add 3. So -2 squared is 4, but there's another negative which makes this -4 plus 3. So altogether -1. Alright, then we plug in -1, so we're going to do -1 squared plus 3. -1 squared is +1, but there's another negative, so it changes back to -1. -1 plus 3 is 2. And we keep going in a similar fashion, plugging in our x values to the function. So there's our remaining y values. When you plug in 0, you get 3. When you plug in 1, you get 2. And when you plug in 2, you get -1 again. Right? Hopefully you guys caught on here that this negative outside gets applied after you square. Okay, this negative does not get affected by this squaring. All right, so let's go ahead and write our points. Let's see, we have -2, -1. We have -1, 2, etc. Now we got to actually plot these on our coordinate grid here. So -2, -1 is right about here. -1, 2 is right about here. 0, 3 is right about here. 1, 2 2, -1. Okay, so these are our sample points, which tells us how the curve is going to look when we connect the dots. Now you may be upset because it didn't turn out exactly like a U shape as we predicted, but in fact it turned out like an upside down U. Okay, so this negative out front is changing it to an upside down U. But it's still essentially the same shape. Let me go ahead and connect the dots here so you can see what our graph looks like. So there's the graph of -x² + 3. Okay, it's still a U-shaped, it's just flipped upside down because of this negative. Cool. Okay, on to a slightly more tricky function to graph, f of x equals √x. You have to be careful with square root functions because only certain x values make sense when you plug them in. So for example, I can't figure out what f of -1 is because that would lead to the square root of -1, which is not a real number. Okay, so when I'm working with f of x equals √x, I'm going to plug in x values that I know the square root of. So what sort of x values do I know the square root of? Well, I don't know the square root of -1. I don't know the square root of any negative numbers. Okay, those are not real numbers when you take the square root. Okay, but I do know the square root of 0. Right? Root 0 is 0. Okay, so I can plug in 0. I do know the square root of 1. I do know the square root of 4. I do know the square root of 9. Okay, so I want to plug in x values that I know the square root of. And these are the first 4 numbers that I know the square root of. You could keep going. You could plug in 16 and 25 and 36. There's a bunch of numbers we know the square root of. But I'm going to focus on the first 4. All right, so let's go ahead and make our table. So I'm going to go ahead and plug 0 into our original function, which was √x, and that gives me √0, which I know the square root of 0 is 0. I'm going to go ahead and plug 1 into our original function, which gives me √1. I know the square root of 1 is 1. I'm going to plug 4 into our original function. I know the square root of 4 is 2. Okay, and I'm going to plug 9 into our original function. I know the square root of 9 is 3. So this is a good amount of sample points. This will give me the general shape of the graph. So let me write out the points here and then plot them. Okay, so we have 0, 0, 1, 1, 4, 2, 9, 3. Let's put those on our XY grid. The first point 0, 0, that's right at the origin. Then 1, 1. Then we jump all the way to 4, 2. And finally we have a point at 9, 3, which is right here. So hopefully this is looking like what we think it should look like. Okay, remember if you flip back to your library of functions that we talked about at the beginning of the topic, the square root function should look like half of a rainbow. Okay, and that's what this is shaping up to be. Let me go ahead and connect the dots so we can get a full picture here. So this is the full graph of f of x equals square root x, the blue curve. There's an arrow at the end because this curve goes on forever. We can keep plugging in larger and larger x values and we will keep getting points on the graph. Okay, example E is getting very tricky. Okay, we need to graph the function f of x equals square root of x plus 1. The tricky part about this is that we have to figure out what the appropriate sample points are. Okay, what sort of x values can we plug in here so that we get nice y values out? All right. When we were dealing with the function square root of x, if you recall, we used x equals 0, 1, 4, 9 because we know how to take the square root of 0, 1, 4, and 9. Unfortunately, those same x values are not going to work because of this plus 1. For example, if we plug 9 in for x here, 9 plus 1 is 10. And then we'd have to take the square root of 10, which is irrational. It's some decimal that never stops. So 0, 1, 4, and 9 were good for square root x, but when you have square root of x plus 1, you want to decrease your x values by 1. You want to plug in numbers that after you add 1 you know the square root of. So let's think about how this works. Before, when we just had square root of x, we use 0, 1, 4, 9. We know the square root of 0, 1, 4, 9. But now we want to plug in x values that we know the square root of after 1 has been added. So for example, we're not going to plug 9 in because 9 plus 1 will give us 10 and we don't know the square root of 10. But we can plug 8 in because 8 plus 1 is 9 and the square root of 9 is 3. We're not going to use 4 anymore because 4 plus 1 is 5 and we don't know the square root of 5. Okay, but we can plug 3 in because 3 plus 1 is 4 and we know the square root of 4 exactly. We're not going to plug 1 in because 1 plus 1 is 2 and we don't know the square root of 2 exactly. But we are going to plug 0 in instead of 1 because 0 plus 1 is 1 and we know the square root. And then instead of 0, we plug in -1. So these are the appropriate x values to use when you're plotting this function. So let's go ahead and do the work. So here's our table. When we plug in -1 to our function f of x, we get the square root of -1 plus 1. So the square root is 0, which is 0. Next, we get the square root of 0 plus 1. 0 plus 1 is 1. Square root of 1 is 1. Then we do the square root of 3 plus 1. 3 plus 1 is 4. Square root of 4 is 2. Then finally, we do the square root of 8 plus 1. 8 plus 1 is 9. Square root of 9 is 3. So now we have very nice sample points to plot. So let me write our points out and then plot them on the graph. So here's our points, -1, 0, 0, 1, 3, 2, 8, 3. And here are the points plotted in the xy plane, -1, 0, 0, 1, 3, 2, 8, 3. Now we just have to connect them with a curve and toss an arrow on the end of the curve since it's going to go on forever. So this is the graph of the function square root of x plus 1. Okay, I want to point out that the right side definitely needs an arrow. Because we can plug in bigger and bigger x values. We can plug in 15 and then that would become square root of 15 plus 1, which is 4, etc. Okay, but the left side does not need an arrow. It stops. The graph stops at -1 here. Okay, if you try to plug in -2 for x, you're going to get the square root of -1, which is not a real number. Okay, so on one side of the square root graph, we're going to have an arrow, but on the other side, we're not. All right, watch out for that. So on to our last function. We're given f of x equals absolute value of the quantity x minus 2. So alarm bells should be going off in your head saying, oh, this is an absolute value function. I know the general shape of an absolute value function because I memorized my 8 basic functions. An absolute value function looks like a v. So at the end of the day, when all is said and done, we are expecting our function to look something like this. Maybe it's moved around a little, maybe it's upside down, but there's got to be a v somewhere after we finish graphing this. Now the next thing you want to notice is this -2 inside of the absolute value bars. Okay, when you have an extra number being added or subtracted inside of the function, that's going to change the sample x values you're going to use. If you remember, when we we're going through the remarks, we plotted the function absolute value of x, right, with no extra number inside. And we use the sample x values -2, -1, 0, 1, 2. They worked very well for the function absolute value of x. Okay. But now that we have absolute value of x minus 2, okay, we're going to need to use new x values. So now, instead of plugging in 2, for example, we're going to plug in 4. Okay? Because if you put 4 in and subtract 2, you get 2 back. Okay? And instead of plugging in 1, we're going to plug in 3. Instead of plugging in 0, we're going to plug in 2. Instead of plugging in -1, we're going to plug in 1. And instead of plugging in -2, we're going to plug in 0. Because if we plug in these numbers, subtracting 2 will bring us back to our good sample x values that we used in this case. Okay. A good way to remember which x values you should plug in is to take whatever's inside of the function and set it equal to 0. See, if you take x minus 2 and you set it equal to 0, you get that x equals 2. That's going to give you the middle x value to plug in. And then you take x values that are a little bit bigger and a little bit smaller. But the middle one should be whatever x makes the inside portion 0. Alright, so here's our table with the appropriate x values filled in. Let's actually do the work and see what we get. So when we plug 0 into our function absolute value of x minus 2, we get absolute value of 0 minus 2. The absolute value of -2 is positive 2. When we plug in 1, we get the absolute value of 1 minus 2. The absolute value of -1 is 1. When we plug in 2, we get the absolute value of 2 minus 2. So absolute value of 0 is 0. We keep going. Absolute value of 3 minus 2 ends up being 1. Absolute value of 4 minus 2 ends up being 2. So there are the points I ended up with. 0, 2, 1, 1, 2, 0, 3, 1, 4, 2. I plotted those on the xy plane, and you can see the v right here. And if you notice, the point of the v is right at 2. That's not a coincidence. That means we chose our sample x values very well. We chose them so that the point of our graph is right in the middle. So now let's go ahead and connect the dots and put our arrows on so we can get a full picture of this function. Okay, so there's our function. Right, exactly what we expected. A nice V. There's arrows on the end because we can go on forever in either direction. Right? It just so happens that because of this -2 inside the absolute values, the point of our V shifted over to +2. Right? And we anticipated that right here. Okay, by setting what was inside the absolute values to 0, we figured out exactly where the middle of our function was going to be. All right, all done.